2. So we're working on chapter 2 and we want to do word problems. And let me get me on the screen there. Sorry about that. And let's start with a screen share here. Pause that. Okay. Sorry, a lot of stuff going on here. All right. And so I am on page, let's scroll up just a bit. 24 in the workbook, page 24. All right. And so we are looking at one-dimensional motion problems. If you need it, I think 2 pages previously, maybe 3. This has got your definitions here on page 21 if you need them. So just be aware those are there. Your equations are at the bottom of page 21 or on the back of your workbook, or maybe you just have these memorized by now. And here's a problem solving strategy. We kind of that was the other section, but this is the strategy we're basically going to use today when we're attacking problems. So when you're doing physics problems, this may not work for every problem and you may not do every step on every problem, but it's a pretty good place to start. Obviously, read the question. Draw pictures carefully. When we're doing word problems, if you can't draw the picture well, you maybe don't understand and you need to go back and reread. When you're reading, you can also use that information to label and identify things that you know and don't know. This is a very common technique in an engineer's life. The first thing they do is they list everything they know. Also, they list anything they don't know or what they are assuming. For example, are you assuming air resistance is negligible? Yes, because this is my class and we will do that for pretty much every problem. Yeah, you might then list useful equations. And before you start doing math, maybe you could just double check you know what you're doing. Just make sure you're solving for the right thing. Once you have all those equations there, try to keep your eye on the prize. Remember, what is the goal? Then this is something that maybe you're not used to if you did problems in high school physics with all numbers all the time. This is huge. We have to learn how to solve physics problems algebraically. Okay, if you don't do this, it's just 1, you're slow, 2, you're bad. Okay, so you've got to learn to do this. All right, and I'll teach you that today. At the end, you do want to sub in some numbers and then check things like the units. Does your answer make sense if you plug in numbers? Things like that. Is it the right size? Meaning, is it the right order of magnitude? Yeah, I once asked a question, how much should it cost pay for the gasoline to cross the entire country? And somebody answered $2.45 billion. That's an incorrect order of magnitude, I think, right? So yeah, and several people said in the millions. I'm like, man, I thought that would be an easy question, but yeah. So always think about reality. Shocking. Yeah, this is a physics class, not a math class. All right. Some people still having some trouble getting in here. If you are bad at this stuff and you wanted to have some if you wanted to have some numerical problems, these first few problems, the 1 1/4, 1 1/2, and 1 3/4, these are some problems where I gave you numbers. So a lot of times students have trouble going straight to algebra and you need a couple of problems with numbers. That's what those are there for. That said, we're back to page 24 now. Our goal is to get used to doing algebraic. Here are the reasons why. It's faster. It's easier to check the units and look for a missed algebra problem. The final result of the given parameters can change. That way you don't have to redo the problem for each new set of numbers. And finally, if you do problems algebraically, you could use that to create a formula in Excel or Python or MATLAB or some other computer program. And we use those algebraic equations to set up the programming and the coding, and it's so much stronger. You could check codes with it, or you can create codes with it. All right, let's start with 2.2 on page, what was it, 24? So I'm going to draw this on my whiteboard. I'll give you a second to get this on your paper in front of you, all right? Get this chair out of here. I was teaching my kids long division last night. That's what that was on the whiteboard, if you saw it. So this is page 24, 2.2. We have a block on a ramp. We're told there's a coordinate system like this, X and Y. I'll show my whiteboard in a minute. Before I forget, I think there's a typo here that needs to be corrected on part A. T is what we're looking for, I think, in part A. So T should not be in the answer. Sorry about that. Okay. What else do we have? Okay, so I'm going to stop and share my whiteboard now. So when I saw this problem, this is what I thought to do. Now let's take a second. Maybe you're like rushing through it, trying to get the problem done. And that's great. I appreciate you being motivated. But let's think for a minute, very briefly, about how you do your work. I want you to do your work in this way because I think over the course of your career, it will reduce mistakes. And that means you'll pass classes with higher grades and fewer attempts. So that's why I'm talking. Now, in this case, oops, let me get somebody else in here. In this case, notice I drew the picture and it's not that small. A lot of people draw like tiny little pictures on their page. Your picture could easily be a quarter of a page or at least a decent size, maybe an eighth of the page, like a quarter of the height and halfway across. If you draw your pictures too small, you get in that habit. And then when the problems get complicated, it's hard to squeeze in your labels. So again, on this problem, you could get away with a tiny little picture, but I want you to get in that habit of drawing bigger pictures so that you have room to label when things get tough in chapter 10. All right. I put down some assumptions. So notice this stuff was written in the problem statement. I didn't need to write it down, but by putting it here, it's on my workspace wherever I'm doing the problem. So I can look at that immediately and remember, oh yeah, friction. I don't need to worry about friction. Oh yeah, I don't need to worry about the size of the box. Oh yeah, the ramp length was L. Now, another thing I might do is sometimes I'll draw this part in red just so it pops. You can use color if you want to. And then in later chapters, I tend to do all of the accelerations in red, or at least for a little while I do. I think that's chapters 5 and 6. So that just makes it stand out a little bit. Is that required? No. But I'm just going to try and do that so you can see the difference. All right. Now, in part A, we are looking for what? What are we supposed to find in part A?
Theta.
Oh, was it theta? Oh, shoot, I misread the problem. So maybe theta was, okay, let me check that out again. So notice this is an important time to reread the question. Oh, I see. So I made a mistake when I gave you that correction. Theta is the variable. I saw this letter T here. We're looking for the angle. So notice a good time to reread is before you do any work. And I just caught a mistake I made. So T should be included, G should be included, and L, but we're looking for theta. Good job. Sorry I screwed up there. But again, that's why we reread the question before going on. All right. So we're looking for theta. And so again, I made a screw up there. It should be in terms of L, G, and T. Sorry about that. My bad. Okay. Now, in this case, that's supposed to say determine, whatever. All right. We've read the problem. We've drawn some pictures. We've labeled some things and listed some things that we know. Let's try and make this a little bit more organized. So I'm going to go ahead and scoot this back just a tad. Hopefully you could still read that. Now, what I want to do is I want to list things that we know. We're trying to do a kinematics equations. And if you haven't done these in a while, I happen to know there's 5 important parameters, 6 depending on how you write it. There's delta x. There's the initial velocity in the x direction. There's v final in the x direction. There's a sub x, and there's time. Now, hopefully they all fit on the board. They do. You don't have to make a table like this, but in my solutions, I tried to get in that habit. All right. So now, okay, we're going to try and describe this thing. Is this thing moving in one-dimensional motion or two-dimensional? What do you think?
One-dimensional?
Yeah. Why is it okay? Like somebody might say it's moving to the right and down. Why is it okay to still call this 1D?
Because we shifted our x and y axis?
Yeah, we rotate it. So this is a trick you can do. You might be saying it's moving right and down. That's 2D motion. But if we're clever, in this case, anytime it moves in straight lines, you could rotate the coordinates so that matches up to the x or to the y axis. It doesn't really matter. All right. So in this case, delta x is a change in position. It's a vector. So to remember, all of these things have an I hat on it, right? There's an I hat that we're pretending is on all of these, but we don't write it because these are vectors. This is displacement, not distance. Initial velocity, not speed, etc. All right, so let's go down here. What's delta x in this case? What's the displacement in the I hat?
L.
L. Positive or negative in this case, according to this coordinate?
Positive.
Positive. So this is a weird one where we say going down the hill is positive. That's cool. How about v initial x? Did it say in the problem anything about that?
It said it was at rest.
Ah, so there's an assumption I forgot. I'll put that up here. So that tells us the initial is probably 0. That's cool. Do we know the final?
Nope.
Nope. Okay, so I'll put a question mark there. Do I know AX?
G sine theta.
It's G sine theta. Is that a known or an unknown? We know this is a formula for it. G is a number we know. Do we know what theta is?
Nope. Nope.
No. And in fact, this is WTF. What to find? I'm sure that's what you were thinking. WTF is theta. So, all right. How about time? Do we know the time in this case? Was time a variable that we knew?
It's known.
Yeah.
It's known, and it's just the variable t. And so this is where things get a little bit weird for students here. Maybe I'll make these all blue here. The idea here is it looks like L and T and G are unknowns. However, you're supposed to know if they give you a variable in the problem and say the length is L, that's a given variable. So L is technically a known. And you could also see right here in this, had I not made the typo, if I say L, G, and T, that's implying for a given known value of L, G, and T. So we're pretending that we do know the numbers for these. We're leaving it in terms of the letters to make it more powerful. All right. Any questions about that? It's kind of a weird aspect when you're first getting used to it. All right. The next step of the procedure is to write down some equations. Well, I've got them memorized. You could look on the back of your book if you want, but I know there's the delta x equation. And when you're doing this, do me a favor, just watch what I do here for a sec. A lot of times I like to leave a couple lines of space before I write the next one. So don't write the equations right next to each other. The reason why, I'll show you in a second. I'm just going to write 2 of these here. Now, on your work, you may want to work down the page or whatever, but generally speaking, when you're working on your own paper, try not to do work in columns. I have to do that because I have a very limited board space, and that's why I'm doing that. Normally, I would work all the way down, then start a new column, work all the way down, whereas you would work all the way down, then start a new page, work all the way down. Obviously, use your discretion. Occasionally, like this, you might put over on the right and then put the rest all the way down or whatever. Okay, I'll shut up now. Many correct ways to organize, but in general, try to work down the page, not back and forth and up and down and all around. Just go down. All right. Let's say there is another equation. It's the V final squared equation. And right now, let's see. I don't actually want to write that because I've run out of room. We'll write it later if we need it. The next thing I like to do, this is a practical step, not in the handout there. The first thing is plug in any zeros because it makes the equations easier. If I plug in anything equal to 0, that gets rid of this. And that gets rid of this. And now, because I left some space, I could literally rewrite the equation right underneath. And notice I still have one more line of room to work. Okay, and here, sorry, it's just such a small whiteboard. I'm used to having 4 huge 10-foot long whiteboards in the room, but this will have to do. So again, what did we do? Picture, labels, list some stuff that we assumed or know, get that into a set of variables in a list, write your equations, plug in the zeros. By plugging in the zeros, that means our algebra steps will be so much easier if we do algebra in the next step. Okay, at this point, remind me what we're trying to get. Oh yeah, we're supposed to get theta. We're supposed to find this. So we need an equation that has theta in it. Let's take a look here. I'm going to go through and do a little step here where I like to check things. Delta x, that is a known. Now you might be saying, wait, it's L. I don't know what L is. You're right, but it's one of the given variables, one of the assumed known variables. This one's 0. A, that has theta in it, so that's unknown, but T is known. So we know X, this looks like a good equation to me. We know everything except for A sub X. Once we figure out A sub X, we can figure out theta. If I come down here to this one, this is unknown. This is unknown. This is already looking bad, but I do know this. So this is not necessarily the best way to start because I have 2 unknowns in it. I have 1 equation, 2 unknowns. I bet you could probably guess if we wanted to figure out V final theta, we could start with this equation, figure out A, plug it into there, then figure this one out if we needed it. I'm going to pause. I have no idea if I'm going too fast or not, but this is a good time for some questions. Anything you want, chat or unmute. All right. All right, and so just so I have room to work here, I'm going to erase this other equation. You might have to like work down the page somewhere else. That's fine. So I'm going to plug in all the variables that I care about. L equals 1/2 g sine theta t squared. And then from there, maybe just to make it obvious, I'll put this in parentheses to be clear. It's not theta t squared. It's g sine theta times t squared. All right. I think from here, it's pretty easy, right? Rearrange this crap and solve for theta. Go ahead and do that really quick. And I'll get the solution up so you can check. And remember, if this is too slow for you or too fast, you can have the solutions open and follow along. So let me get that here. Whoops. What was this, 2.2? Yeah. So this is just kind of walking you through. There it is, right there. Make that a little bigger. Whoa. Let's make this 250. Make that 230. There we go. Sorry about that. There it is. And so you could see I tried to be very detailed in the solutions, saying where I got these things from. So use those solutions when you're checking your work. Try to do it by yourself. If you fail completely, then look at the solutions. But at some point, you got to wean yourself off the solutions. People like, oh, I could do physics. I'll just follow the solutions. That's not doing physics. That's copying physics, which is a good start. It's a good start, but it's not going to get you all the way on test day. All right. What's a smart thing to do after you get this equation? What's something
Check
I would,
units.
yeah, check the units. So let's think, what are the units? This might be a little bit weird to some of you. What are the units of theta that we assume?
No units?
Yeah, no units or radians. So either one of those. So I'm going to say no, we do not say degrees in general. So that was good. All right. So it turns out if you want to do calculus with angles, you need to have it in radians. So that's ultimately why we say it's in radians. Now, that doesn't mean we aren't going to answer in degrees, but for the unit checks, we use radians for unit checks. So that means, okay, what are the units of a function? Does anybody know?
None.
Yeah. So functions have no units. That was a chapter 1 question. If you haven't got there yet, you'll see it. So function have no units. So that matches. What about the argument of the function? This, let me get a different color here. What about the argument of the function? This stuff that's inside the function. What are the units of that?
Radians?
No units. Yeah, and so you could argue for a trig, we should be thinking radians as well. So let's say radians or just no units, either one. Now, other functions would be no units, but trig functions are special. We say their no units are no units of radians. All right, so that means we need to check this pink blob to make sure it has no units. Otherwise, this won't work. What are the units of 2?
No units.
No units. What are the units of L?
Meters.
Meters, it's a length. And then G, we'll just write it out here. You got the right idea here. And then time squared. It looks like the units check, agreed? So that's a step I may not have time to go through every time with you, but usually whenever we're doing work on the board and we've spent, 10 minutes deriving some formula, it'd be crazy not to check the units before moving on. The reason you check it is it can sometimes help you catch a screw up in your algebra. That's the real reason we want to learn this. It helps you get a check on your math. There's no guarantee that having correct units gives you the correct answer, but you are guaranteed to know it's wrong if you get the wrong units. So it can at least verify that you're not completely wrong. Questions about that? Here's that written out if you need it. All right, so the unit math. And then notice I do some reality checks here. What happens so this is, if you're wondering what I mean by a reality check, this is what I mean. What should happen if L is increased? I think if L is increased, the time will increase. Okay, blah, 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 blah. So, oh, there's a square root in here. So this is kind of showing you that reasoning. So think about this. If the length of this thing is increased and the time stays the same, that would be a different one. Or you could say, what if the length is increased and the time is also increased? What should happen? Or what would happen if we did this thing on the moon? Right? If we did this on the moon, G would be a smaller number. If G is a smaller number, that makes this number inside bigger. That means you need a steeper angle. So those are the kinds of things that you could think about. What if it's parallel to the ground? Oh, okay. So if it's parallel to the ground, the angle's 0 degrees, none of this stuff makes any sense. So I don't know if you could tell here. Sometimes it's easiest to do reality checks with this formula. Sometimes it's easier with this formula. So when you're doing your reality checks, you could do it on an intermediate step if you want. Okay. So obviously, if you make this longer, you'd expect you might need more time. And so that seems plausible. Or like I said, if you have a smaller number here and you keep the time the same, maybe you'd need a longer ramp or a different angle, something like that. Go ahead. Question? Oh, my bad. All right. And so that's the main difference. Then that's the main thing I wanted you to get used to, is doing problems algebraically. Let's maybe look at one more here and just see how you do. Oops, let's get back to this one. Notice in this one, I changed up the coordinate systems. Okay, so if you do this one, things are going to be a little bit different. Let's try 2.3. All right. And instead of doing the whole problem, I'm most interested in setting up the problem. I think you guys could do all of these other steps on your own at home and check it out. We did all the setup. So, okay. So now we're moving on to 2.3. I'm going to draw it, and I'm most interested in seeing if you set up the problem right. Try to make your work look pretty, organized, neat, thorough, clear, concise, and complete. So we're doing 2.3. I'll show you my whiteboard in a minute. Okay. Just making sure I'm reading it one more time. We got the block, it's kicked, it slides up the ramp. Just after the kick, it's moving up the ramp length L with some unknown initial speed V0. Aha. Okay, so the acceleration after the kick is still G sine theta directed down the ramp as shown. Slides 3/4 of the way to the rear. Okay. All right. So this is just me getting that problem down. And so I'm writing it slightly differently this time. So here I'm making this explicit early on. I'm assuming it's a frictionless ramp. Why? Because it says it's basically implying we're using the same ramp as the previous problem, which was frictionless. So I think that's reasonable. So yeah, that's an assumption I made though. So I wrote down that assumption. I write what was given in the problem, L, G, and theta, and what to find is V naught. We were told that's unknown, and somewhere it has to find that. The next step is going to be making that table. Again, for one-dimensional motion, some of you might be used to doing things this way, where you say X initial and X final v initial x, et cetera, et cetera, et cetera. That's totally fine. Now, keep in mind that these two things combine to make delta x. So sometimes I just like to do it that way. Sometimes I like to do it this way. So in this problem, just to mix it up, I'm going to do the x initial and x final method, all right? So let me do it this way. And I need a little bit more room, so I'm going to move this up. All right. So right away, I'm looking at this list. I'm like, well, I clearly do not know time. So I'm going to say time is an unknown. All right. A sub x is actually known or unknown in this case?
No.
Known. So is it g sine theta?
Negative. G sine theta.
Negative. Good job. So look at this case. We know that this way is called positive, but it's accelerating down the ramp. Remember that there's an I hat implied on all of these. So anything that's going this way would be a positive V or a positive A. Anything that's going that way, opposite the coordinate, would be a negative I hat. Nice job. Nice job. All right. So is the initial velocity 0 this time?
No.
No, it's V0, right? And that's what we're looking for. Nice job. Okay. What's a good thing? We could choose x initial pretty much in this problem. I think it's reasonable to assume it starts from the origin. So we could call this the origin here. So I'm going to choose that. You could call it differently, but I'm going to say this is 0. All right. I'm assuming x initial is the origin. If x initial is 0, what is x final?
3/4 of L.
It's 3/4 L. If you look carefully, it doesn't make it all the way up the ramp. It says the ramp is L, but this thing only makes it up part of the way. So maybe it would make sense to include that in our picture. And then you could label that like this, 3/4 L. That way we don't get confused. So having that information in your picture is a lot stronger, and it explains why this is 3/4 L. Imagine you look at this 2-3 months from now, and I ask you to explain it. If you have this picture here, you'll be like, oh yeah, that's why I got 3/4 L, because it only goes 3/4 of the way up. If you don't have that picture, this might not make sense why you did it, and that slows you down. And it's not that you can't figure it out, it just wastes your time. Okay, V final X, what is that?
Would it be 0?
How do you know it's 0?
Because it says it slows to a stop at 3/4 L.
There you go. That word stop. Now, what does it do right after that?
Starts accelerating in the negative x direction.
Good, good, good. And I'm just going to say it stops and reverses direction. That's the same thing as what you just said. Agreed?
Yeah.
Cool. It's saying it a different way, but yeah, basically whenever an object reverses direction at its max height or its minimum depth or whatever, whenever it hits an extrema and reverses direction, this is true. So this is something you're supposed to kind of know from the words. All right. What's the next step? What's the next thing we would do in the process?
Reread the question.
Yep. And then let's say we reread it. We know we're looking for V naught. Then what?
Write out the equations.
Yeah. So now just because I wrote the initial and final, I'm going to write it out this way this time. Right. And then I would probably leave some space. And let's just do, this time I'll do this one. Obviously, there's the V final equation. I might squeeze that in down here, but I'm running out of room. All right. Let me just scoot this back just a bit. So maybe down here, I do the V final X equation. Sorry. All right. All right. So it's always a challenge. If I push it too far back, the text gets too small in the live stream, but we're just doing the best we can here. All right. So I wrote some equations. Oh, whoops. I guess if you want, you could get rid of this delta x, right? What delta x, isn't that just x final minus x initial? What is the next thing you should do?
Plug in zeros.
Exactly. We don't want to just go right to the algebra, plug in the zeros. Now, this time I'm just so limited in space. You should write it on the next line. I'm just going to erase anything that's zero. Sorry about that. So that's 0. V final is 0. Oh, cool. So again, you should not be erasing like this. You should work down the page. Did I miss any? I think that's it. I'm just going to rewrite that without the parentheses now. Sorry about that. I hate erasing, but I think that's good. So before you just start grabbing an equation, let's at least look at it and see which one we think might be most useful. So by doing that, I'm just going to check. This one's known. V initial is unknown. Time is unknown. A is known this time. This looks bad. Too many question marks. That's basically it, right? That's too many things in this equation I don't know. And just for this part, I'll bring it a little closer so you can see it. Gosh, so much glare. All right. Next, here we see V initial X is unknown. AX is known. X is known. This is the one to go with, right? We should be able to get V initial very quickly from here. And then obviously, once you get really good at this, people, you may not want to write this all out every time, but as a beginning student, you should probably do this every time for a while. Eventually, you'll get better at it, and then you can do this check in your head, and then instead of writing every equation every time, you just grab for the right one. But you might as well get these memorized. The easiest way to memorize is have to write them for every problem for like 10, 12 problems, okay? So I recommend writing the equations, checking this every time, and then on your test day, you don't need to do all that. You could just grab the right equation if you see it. Okay, that's just, I don't know, my advice. You can listen to it or ignore it. I don't care. All right, so that means let's plug in here. This is our equation to go with. So we say 0 is equal to V0 squared plus 2 times, that's negative, isn't it? The minus signs are super important. I'll show you why. There we go. And so I don't even need this equation. I'm going to erase it so I have some room to work. Let me see if I can get rid of some of this glare a little bit. If I lower this and angle this slightly, just glare. Whatever. All right. In this case, you could clean this up a little. But I'm going to do things this way. I'm going to bring this V0 over to the other side first. So that would be negative V0 squared. That'll give us an opportunity to talk about order of operations. Over here, the 2 times, that looks like negative 3/2 GL sine theta. Sorry for that glare. Now, I want to talk about this. I'm circling it right now. Is that thing in the circle here positive or negative?
Negative.
Negative. You have to remember PEMDAS is order of operations, right? So first you do the exponent, then times -1. Just think about it. What if you plugged in a number here, regardless of its sign? Let's say it was negative 16. When you square it, that would be positive 256. When you bring it to the other side, shouldn't it be negative 256? So it's important to know that negative V0 squared is equal to the negative of V0 squared. Just remember that. This is correct. Oh, geez, that glare. Sorry. Is that better? A little? Sorry, it's so dark, but negative V0 squared is not equal to negative V0 squared. Right? So this is true. This is not. Just try to, it shows up a lot. And if you're in a hurry, you might forget that. You probably know this already. I'm just trying to warn you, that's a common mistake. That's all. Okay. Remember that you can do this. You cannot do that. All right. And then from there, here, because this is out front, I could cancel that. I could solve for this. All right. And so in this case, we have one last thing to think about. Every time you take a square root, especially in kinematics problems, make sure you always at least think about the plus minus signs. Okay, when we're thinking about the plus minus signs, which root makes sense for this problem? Should I use a positive or a negative answer? And why?
Positive,
Why?
because it's being kicked up the ramp.
Exactly. V0 was the initial velocity. Look, isn't V0 supposed to be positive? Oh, shoot, sorry. Isn't V0 supposed to be positive from our initial picture? We said this way and this way. That's why we take the positive root. If I had solved this other problem, maybe in a different problem, we might solve for V final with the square root similar. V final would end up being a negative answer. And that's very common that sometimes when you're doing these problems, this equation, a lot of times you need to remember to take the negative root because sometimes velocities are positive or negative. Again, sometimes when solving this equation, you do have to remember to take the negative root. In this case, we didn't have to. Let's go back down to here. All right, what are some things we should check right away? Check the units. So this is the square root of numbers, no units. Sometimes you'll notice I put a little end to my square roots. Well, that's meters squared per second square root. Meters per second. Is that looking good? Looks good to me. Wait a minute. Wait a minute, everybody. I thought gravity pulls down. Isn't G a negative number? Isn't it negative 9.8?
No, G is always positive.
Yes, exactly. All right. So I'm trying to get you the common things. Sometimes students, I know I sound like a broken record when I say this all the time. You would be surprised on test day how many people screw this up. G is not gravity. G is not the acceleration due to gravity. G is the magnitude of the acceleration due to gravity. It drives me crazy when people can't figure out G. If there's one thing you want to do to piss me off, just say G is gravity. I'll be like, that's cool, minus 10 points. All right, so it just drives me nuts. G is not gravity. It's the magnitude of the acceleration due to. Enough on that. All right, what do you think? So far, so good? Let me get the gallery view and just see. Okay, any questions right now?
So on, I think like one or two questions, when it concerns like, I think like 4 and 5, G sine theta kind of converts into negative G over 2. Why is that?
Oh, so it turns out in some problems, they use a different coordinate system. If you have different coordinate systems, remember the magnitude of G is going to point downwards. Sometimes your coordinate system also points downwards and you'd use a positive value. Sometimes your coordinate system points upwards and you might use a negative value for that. So I guess I could say it like this, Nick. Let me go to my whiteboard. Whoops, crap. Yeah, good question. This is a sneaky trick here. I'm going to erase all this one. We've got the answers in the workbook if you need them. If I erase something, remember, you got the answers. If you're tired and bored and this is too easy for you, remember, you can work ahead on the homework problems instead of listening to me, and then just kind of keep Zoom on in the background in case something important like this comes up. All right, so I just want to point out the acceleration. Like, let's say you have a normal coordinate system, X and Y, and you have something that's falling down under the influence of gravity, right? So maybe there's a ball here and it's falling down or something. So great. Or maybe it's a ball that got thrown upwards. Who knows? I just want to point out the acceleration is G in the negative J hat direction, or sometimes that's negative G J hat. So sometimes we'll write this as AY equals negative G. And so I just want to point out, that's a sloppy letter Y. I want to point out that A and G are different. A depends on the magnitude and the coordinate system direction. So here, because the coordinate is up, AY is G in the negative direction. That's why you get this negative G. Nick, did that address your question?
Yeah.
Okay. And we will revisit that in chapter 4 and later in this chapter too. Is that good for now?
Yeah, I also pointed out that like sometimes it gets divided by 2.
That's because, oh, I see. Remember the delta X equation. So in this case, remember the equation has a 1/2 in it.
Right.
So when you plug that into there, you get minus G over 2 T squared.
Okay.
So it's, yeah, so the reason I like to write it like this is some problems don't have G in it. And so for those problems, it doesn't make sense to just immediately jump to that.
Right.
Okay. What if you're doing a horizontal problem, or what if you're doing a vertical problem and it's not free fall? So
Right.
this can happen. So I like to take the extra step of first writing down what A is. And then if it's a normal free fall problem, sure, you could just skip right to that. But I usually do this extra step of saying AY is this, because sometimes in kinematics problems, you will actually flip the coordinate system like this. If everything in the problem is going down, what if you take a rock and you throw it downwards? This is a better coordinate system where Y points down, because then everything's positive and there's no negative signs in the entire problem. That's one less way to make a mistake. So sometimes weird coordinate systems are useful. Is that good on that, Nick?
Yeah.
Right on. Other questions? Right on. Okay, so this is all well and good. Now, usually this next step is where students get toasted. All right, so let's take a look at, let me find a good problem to do here. Come on. Geez, this thing's slow right now. I think it might be 2.36. Let me see. Oh, come on, computer. Whatever, I'll just do it this way. Oh man, those are good problems right there. Okay, so page 41. We're going to do page 41, yeah, 2.36. This is the cop and the speeder problem. So what happens now is we see we're going to have 2 different one-dimensional motion problems, and we're going to try and keep track of these things. So if you want, you can actually open up the solutions and follow along if I'm too slow for you. And in case you're wondering, we are going to take a break, but it's going to be at about 1:20. So we've got about 20 minutes to the break here. All right. So hang tough if you're getting tired. I will give you a break at some point right before the group activity today. All right. So we're looking at 2.36. And I know you're probably excited to jump right to it. Let's kind of talk meta here. What is the first thing do you think a physics instructor would want you to do with this problem?
Draw it out.
Draw it out. If you don't draw it, you have nothing to label, and that's really where students screw up. People try to do everything in their head, and make sure you try and draw it slightly large, because just trust me, you don't want this to be too small. You've got two things, you need to be able to label it. All right, so go ahead, draw it, label it, try and list your knowns and unknowns. Before you get too far ahead, this is something, well, let me just show you the solution to show you what a good way to make this might look like. So this is 2.36. You don't have to do things my way, but I do think for a lot of you that are starting, oh my gosh, is this thing going to go? Sheesh. Come on, Zoom. Having some trouble today. There we go. So let me just hit Control F. What was this? 2.36. All right. So notice I drew a picture, and then this is what I was going to recommend to you. Split up the page and label things differently. So for example, notice I have a section for the cop here. And I just called the cop number 2. And I have a section for the speeder. So I did subscripts number 1. So notice I have 2 sets of knowns and unknowns, one for the speeder and one for the cop. So obviously you could do this on your own. You don't need to read my screen, but so go ahead and give that a shot here. All right. And let me go back to the question. Oh, whoops. Gosh, sorry. It's more important to learn how to set these up properly, because the rest of it's just algebra if you can do that. Okay. That's what we need to focus on. Sets you up for good habits as a future engineer too. Neat work. It's 2.36. Another thing you could do is, if you want, you could use different colored pens. You could use blue for the snail and red for the cop, or vice versa. Okay. And I think I used number 1 for the snail and number 2 for the cop. So I'm going to label that in my picture. Okay. Want max distance between. We're told the snail is driving at speed v. Constant speed. Passes the cop without noticing her. Cop accelerates from rest. All right. This is tricky. There's a key thing you're supposed to know. To save us time, I'm going to tell you the fact you're supposed to know. The maximum distance between occurs at what point? Well, I guess I am going to ask. How do we know the maximum distance between these two things? What do they have in common?
The velocities have to be equal.
Yeah. So if you set their velocities equal, that's when the cop stops losing ground and starts to gain ground. I could prove that to you in a minute, but just know that. And then just know that on question B, it says how far when she finally overtakes or catches up to. That means they have the same, what?
Position.
Yeah, the same X value or position or delta X or whatever you want to call it. So just be aware in parts A and B, that is a fact you're supposed to memorize for test day, just in case you didn't know that. And this is not necessarily obvious. A lot of people have trouble with this first one for some reason. So if you did, don't feel weirded out by that. A lot of people have that trouble. Okay, so that is how I know this one should also be moving with speed v. If it helps, think about this. A second later, the cop speed will be bigger. They're going to close the gap. I think I made a video in the lab and I can find it and send it to you, showing a simulation of, well, just a real world situation like this. I'll try and get that at the end of the problem. All right. So in this case, now I'm going to do delta x1, v1 initial x, v1 final x. You can reorder the subscripts. It doesn't matter. Let me get closer just for this part. You can race me now. You don't need to listen to me. You can just do your own thing. Sometimes they have different times. Sometimes they don't. It's all about being neat. Subscripts are your friend. Okay. Whoops. Get that glare off there. Okay. So in this case, delta x1, I don't think I know it. V1 initial, that is just V. V1 final, let's think. How about A1? What do you guys think? What about V1 and A1 here? V1 final X and A1X for this speeder.
Isn't V1F?
Oh, go ahead.
Isn't
Sorry.
V1F just going to be V?
Why?
Because it's constant?
What? Okay, true. It's a constant speed. So what does that tell you about A1X?
0.
0. Nice. Good. So notice the wording of the problem is really critical. The algebra is easy for most of you. And if not, it will rapidly become easy. So don't worry about the algebra. It's really critical that you understand how to read the problems and see what words in the English language tell you which things are 0 or not, or how to set up the problem. If you don't have that piece, these problems get really difficult really quickly. Reading is really important, and interpreting that using the language of physics. All right. For this one, I'm just going to call this one, I don't know, but I'm going to call it T. Just the reason I'm going to call it T, shouldn't both of these be moving for the same time? So I don't know what T is, but I just want to get rid of the subscripts. So again, you could have left it as T1 and T2. Whoops, there's no X on the T. Sorry about that. But why not just call it the letter T? This is useful. We know they travel for the same amount of time, okay? So we don't know what that time is, though. Next, X2, I don't know it. V2 initial X is what? V2 initial X.
0.
0 starts from rest. V2 final is?
V.
V. And that was from this piece of information. Max distance between, that's what gives us this. Those are the key words. And then AX is, I think, just A, right? Do we need to worry about any minus signs for this problem?
No.
They're all going right.
No. So that we're lucky in this case. We set it all up so it's moving to the right. Technically, I should draw a coordinate system. So I'm going to assume that way's in the X direction and this way's Y. But since everything's moving to the right, we're lucky. We don't have to worry about minus signs. All right. What would be the next step? What's the next step in the process? There's many correct answers. So just what would you do next?
Solve for delta X.
In order to solve for delta X, you need the
Equations.
Equation. So yeah, solve for delta x basically means write down the equation and solve for delta x. That's great. So which delta x is the answer? Is it delta x1 or is it delta x2?
Would you combine them?
How?
Add them together?
Nope.
Oh.
I want the distance between them, right?
Delta x1 minus delta x2.
Yeah, because isn't this delta x1? And isn't this, sorry, I'm running out of room here. It's not perfect. If we ignore the size of the car, I guess I should have gone front to front, right? So let me draw this slightly better. All right, if I start here at the front of the car, I should also go to the front of the car. That's what I'm saying. So the distance between would be the subtraction. Distance between would be the bigger one. In this case, oh, wait a minute. Did I mislabel those? I did. Wasn't the blue one x1? Sorry about that. And this one was x2, wasn't it? So distance in this case would equal delta x1 minus delta x2, not plus. So you had the right idea, though. Now, if you're not sure which one's bigger, what could you do so that you don't have to think? I'll tell you. Absolute value. Oh, yeah, you got it. Yeah, so if you take the absolute value, we wouldn't have to worry if I accidentally put the bigger one first, right? That's all I was saying. Because distance is positive. That's why it's okay. All right. That's the trick. I'm going to pause here. Again, I'm trying to show you the setups, and I know that you could do the algebra at home. I think this is one of your required problems, so we kind of got you set up. You could do it later. But I don't know. Any questions about this? Let me go to the gallery view here. Anything? Or you could throw it in the chat, or I know you're probably really tired. Okay, so that's great. Let's look at the next part. The next part says, how far when finally overtakes? This is my question. If we're looking for part B, can I use the same set of crap that I have on this whiteboard? Would this set of knowns and unknowns work for part B?
No.
No. Right? The picture doesn't match. So what do you have to do? Start all over. Now, to be honest, on test day, I would probably give you one of these two parts. And I don't know if you've noticed this. Sometimes there's parts A through H or A through M. There's no way I'm going to do that on a test day. I'll probably do parts A, B, C, D usually. Sometimes I'll even have a part E or F, but most of the time, test questions have significantly fewer parts than this. This is to help you learn, so I'm showing you every possible way I might do it on a test day, and then I test you on a subset of that. Just know that. All right. So to do part B, let's, in the interest of time, you could think, I'll give you a minute. All right. Take a minute. Think how you would set up part B. All right. So I've got the clock there. So how would you set up part B? What would change? What wouldn't? You don't have to write it out. You could just think about it. Which things would change? Which things wouldn't change for part B?
Well, delta x1 and delta x2 are equal. And then final velocity for
Do we know what they are? Do we know what x1 and x2 are? Is it a known? We know they're the same, like that's Esteban talking. Esteban said, we know that in part B, these two things would be the same. What I'm asking is, would they be a known quantity that are equal to each other, or an unknown quantity which are equal to each other?
unknown.
Unknown, and that's one of the things we're supposed to find. All right. Somebody else, is there anything else that would change? Would this stuff change?
Yes.
To what?
V would be the initial, and we wouldn't know the final.
Yeah, okay. Wait, V would be the initial?
Yeah, it would be the initial. Because you have to
I would
find-
say you could still start it from rest and just go all the way to here. So I would still use 0, this, and this. Otherwise, you're having to split this into 2 chunks, and that makes the problem harder. So I would actually start at the same point, leave this initially at rest, but this would change. The acceleration would not change. Does that make sense? Because then what you're trying to do the problem from here to here, which then you have to add that to your answer from the previous part. Now think, what if you accidentally made a mistake in here? Then your work for this part, even if you do it all correctly, would be based off a wrong answer. By starting all over and not using this intermediate step, you could get part B right without getting part A right on test day. That's kind of the thought process there. Is that good, whoever that was?
Yeah, that makes sense. Thank you.
Right on, right on. Not that what you said was incorrect. I think it's maybe slightly slower and maybe prone to making more mistakes. That's all. That would have been a correct method. All right. And then over here, I think all this is the same, right? We still don't know what this is. These happen to be equal. Let's go take a look at the solution now. Obviously, you could do this on your own, but let's just see if something pops out. So blah, blah, blah. Notice I just redid it from scratch. And then, okay, so now notice this is not the same time as in part A. These are not the same delta X's in part A. So you could do this a different way, but there we go. All right. Okay. Now, we're getting close to time here. Let me see. I want to show you how this gets nasty in a hurry. What if we had a situation? Let me start with a screen share. You're probably thinking, oh, I did this in high school. I know what I'm doing. Ha 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 ha. Okay. Yeah. So if you can do problems 2.37 and 2.38, then you know what you're doing. 2.36 is the easiest cop and the speeder problem. So these ones are significantly trickier, and they require you to understand everything really well. Let's look at 2.37 together and just kind of analyze why it's different. Speeder is driving at speed v, passes the cop without noticing her. Cop accelerates from rest until reaching a speed that is 25% greater than the speeder. Then the cop continues at this rate. Okay. How many stages are in this problem? By that, I mean, how many sets of knowns and unknowns are you going to have to write? How many sets of equations do you need to write? What do you think?
3.
3. Let's look at the solution, and I'll show you how I chose to split this one up. You can learn a lot by this, okay? So let's look at 2.37. By the way, if you like this problem, that's one of the options for tomorrow in lab. You could learn how to make these plots, all right? So look at this one. This is how I chose to split it up. You could do 4 maybe, I don't know. But to me, it made sense to do this. Oh yeah, the max separation is no different because we'll get into that in a minute. But let's look at this one. There's the speeder who moves at constant speed forever. The cop has an acceleration stage, then has a constant velocity stage. Notice 25% more is 1.25 times v. So that's how you get that 25% more in there. All right. Now, notice here, I gave you some of the work, but I didn't do every single step. But you can see one way of solving this is shown below here. All right. So notice the cars have the total time at the same total time when they meet. So these two, whoops, let me do this. Let me get my marker here. These two times should add up to this time. That's what this equation is saying right here. So notice we're getting more and more equations when life gets realistic, right? Realistically, cops do not accelerate for infinite time. Usually at some point they get going really fast and then they stay at that speed. All right. Furthermore, we get this ugly equation here. The two distances here, if they're going to meet, when they meet, now we're talking about when they meet, those two will add up to here. So I'm looking at part B to be clear. Notice we get these two constraint equations. These are equations that constrain the variables in the problem. They limit the values that things can be, right? They constrain each other's equations. So these constraint equations are things that relate to the words in the problem and physics. When they meet means they have to have the same delta x. Okay, and this one is supposed to be, I guess, just an assumption you make. They're traveling for the same amount of time. If they're traveling for the same amount of time, we know that the two stages for the cop. I'm going to pause. Any questions on that aspect? All right, here's a bonus question. Up here at the top, this says we don't need to worry about stage 3. That's basically what it's saying. Agreed? Why do we not need to worry about stage 3 for max separation? Why do we not need to worry about the cop moving at constant velocity for part A?
Because max separation happens when the velocities are equal, and that happens in stage 1.
Exactly. So we know that the cop is accelerating at constant rate all the way up to this speed. Well, since they reach max separation at V, I know the cop is accelerating the entire time until they hit max separation, plus even a little bit longer. Excuse me there. So that's good. Nice job. All right, one more. Sorry. Look at this one. Suppose a speeder is driving at speed V. The cop takes some time delta t to put away his equipment before starting to accelerate. Ooh, the cop is now a dude. Okay, so the cop accelerates from rest with constant acceleration, until reaching the speeder. That period shouldn't be there, sorry. Whatever. For ease of communication, let's call the point, okay, the origin. Okay, so think to yourself for a second. Don't blurt it out loud. Think to yourself, how is this problem going to be different? How many stages do we need? What are they listed notes? So take a second. I'll give you a couple of minutes here. Maybe don't look at the solutions right away and think how you would set it up and see if you can come up with some questions for me, like what you don't understand or what assumptions. So think for a minute. I'll give you until 1:20. And if you have questions, you can ask now or chat now too. You can ask me anytime you want.
Where would delta t fit in the first stage?
Ah, yeah. Delta T. Well, let me ask you, I don't know who that was. Who is this?
Jose Valencia.
Okay, so Jose. So I kind of walk me through what were you thinking, just so we get there, and that'll give other people a chance to catch up. I think you're kind of ahead here. What were you thinking here?
Well, it says he takes delta t time to put away his stuff before accelerating, so I'm not sure if that's time or if that's supposed to be like maybe initial velocity.
Okay, it's a time, right? This is a time, but it's not the time that the cop is driving. Do you agree?
Right.
So it's like, how do we get this delta t into the equations? Well,
Yes.
let me ask you this. Who is are these two people going to drive for the same time? Are the speeder and the cop going to drive for the same amount of time?
Yes.
They will?
Until he catches up to him?
No.
No.
The cop drives for less time because the cop spent some time putting away the gear.
Oh, that makes sense.
So T1, let me use T speeder. TS, should that be bigger or smaller than T of the cop? We know they're not equal. They're not equal. Which one should be bigger? Who drives for more time?
Speeder.
The speeder. So doesn't that mean it's the cops plus a little bit? Does that make sense? Was that Jose's? So Jose, does that address your question?
Yeah, that makes sense.
And that basically, if we go back, we call this T1 and T2. Now, somebody else might say, no. I say the cop should be the time of the speeder minus a little bit. And that is also a correct way. Do you agree those are identical statements? Or
Yes.
equivalent statements, not identical. So that's the trick. So now you know how to handle this. If the cop accelerates, then goes to a constant, you can do this one. And then I had a bunch of students one year that weren't listening to me and weren't doing their homework. Not a good idea. So I'm like, okay, do these three problems. And I just took the 2.37 and 38 and put them together. So there was a max speed and a time delay and put it on the test because I knew nobody was doing their homework and only one person in the class got the test question right. So if you're wondering if that's the kind of guy I am, that's the kind of guy I am. So make sure you do your homework or you will be toast. All right. So I know it's a lot, but you just can't learn this without doing the homework. Yeah, so I was actually pretty impressed that student got it because I was like, all right. And he's like, yeah, it was exactly like the homework. I'm like, okay. So if you do the homework, you're going to rock the tests. If you don't, you're going to bomb them. And if you copy off the solutions all the time, you really didn't do it. You don't know anything and you will bomb the tests. You've got to learn to work yourself off the solutions. All right, not trying to scare you. I'm just trying to, I don't know. I hate using fear as a motivator. I don't know. I think that's an aspect of my growing up so white. But just try to do your best to not use the solutions all the time, so that when you go to practice the test, you're not, oh crap, I used the solutions the whole time. I don't know anything. That's what I'm worried about. Okay. All right. Let's see. What else do we got here? Let's see. Oh my gosh. I think we got this done here. That's cool. I don't know. So let's see. At 1:45, we're going to start the group activity. And that means we have 13 minutes to do whatever you want. Do you want me to just pick a problem that's off the required list and we start looking at it? Does that sound good? Okay, so let me get out that required list. Where did that go? Where's my paper? All right, just try and help you get as much homework done as possible in class. Let's see. Whoops, that's the syllabus. Whoops, where's that other file? Oh, here it is. Okay. Okay, so 36 and 37 are required. Let's see. I tell you what. Let me see. Let's just do 37 and together, right? Otherwise, I'm going to spend time looking for it and waste time. So let's do that. Let's look at 2.37 and just try and set it up. We were just looking at it, so let's just get somewhere. All right, I'll bring it back up. Okay. So, yeah, let's do that one. 2.37 or 2.38, whichever one you want to do. I'll probably start looking at 2.37 and write it up more thoroughly here. Oh, wait, we just did that one. Let's look at 2.38. Sorry, 2.38. I said the wrong number. 2.38. And again, let's focus on the setup of this problem. Eventually, you'll learn that that's where the learning happens. Okay, so got a cop here. So 2.38. I've got a cop and a speeder. Man, look at that S car go. Finally got the joke in. It's the classic physics joke, the cop and the speeder. S car go. You know, jokes on Zoom work better when you repeat them over and over and over again and no one laughs because they're all just boxes on screen. That's really the key to humor. Oh, I'm losing it. Okay, so this cop is going, or the speeder's going at constant speed v. We're going to label that one number 1, the cop number 2. This one waits time delta t. We already discussed time 2, or time of the cop, is equal to the time of the speeder minus a little bit, or time 1 is equal to time 2 plus a little bit. Either way is fine. Then this cop's going to accelerate. All right. So we're going to do, let's do part A. Okay. Max distance between. Okay, I'm going to share my whiteboard now. So I'm just kind of making some notes here. Obviously, you've got the solutions, but let's just try and play with it live because sometimes you see more when you're seeing it written out. This is what I drew. We want the max distance between. We're doing 2.38 part A. We know that max distance between means the cop and the speeder have the same velocity, so I drew that over here. I'm labeling the speeder number 1 and the cop number 2. So I know this is what's going to happen. And this is a new constraint equation. We know either T2 is T1 minus delta T or T1 is T2 plus delta T. Generally speaking, I like to avoid minus signs just because that's one more thing I don't have to think about. So I'll probably use this. You could use whatever you want. They give you the same answer. So now I'm going to write this out. I know that delta x1 is unknown. V1 initial is equal to V1 final is equal to V. The acceleration of 1 is equal to 0. And the time of 1 is equal to I don't know. Over here, I know delta x2 is I don't know. I know that V2 initial equals 0. And I know V2 final is equal to V. Otherwise, they wouldn't hit max distance between. I know that A2 is equal to A, and T2 is equal to I don't know, but I can use these relationships here. So since I'm using this one, again, so I'm saying T1 is T2 plus delta T. Somebody else might have said T2 is T1 minus delta T. But somehow we have to get that delta T in there because that is a known. That is something we know. From here, the problem is exactly the same as every other problem. Write down your equations. Well, I'm just going to get rid of that image so I have some space. So I'm going to write down the... Now I have a little bit of space to write. So, you know what? I'm going to write down the velocity equation first. I don't know if it's a good idea or not. I'm just thinking out loud. But I do know that this velocity is equal to that one. Maybe that'll give me something. Maybe, I don't know. So I'm going to write that equation down first. V1 final equals delta x1. Whoops. Well, actually, there's nothing to write there, is there? So I'll go over to here and write this one. Sorry, I'm just thinking this through out loud, looking for clever ways to do this one. I know that delta x2 is equal to 1/2 at squared. Oh, but t2, yeah, okay, so that's going to be here. You know what? Sorry, I'm just changing my mind. I'm just having fun with this problem and doing it like you would. I'm going to change this one to t1 here. That's legal. I don't know. We could write it this way, and then all the equations are in terms of t1, and then I got to remember to square it. So this is going to be the ugly part. But that doesn't help me get anywhere, I don't think, because I don't know what x2 is, and I don't know what t1 is, so that didn't help. That was dumb. Oh, well, let's keep going. Let's write v2 final is equal to 0 plus a, or let's just write it this way. Oops, v2. This one I think is actually going to get the job done right here. This side I know is v. This is 0. A is known. And then look here. T2 is, what is that? T1 minus delta t. At first, this may be like, what? How is this problem done? Look, v is a known, a is a known, delta t is a known. That means I could solve t1. Once I get t1, I could figure out t2. Once I know t1 and t2, I could get x1 and x2. The problem is done. Now, obviously, there's work to be done here. I'm going to pause right now and see if there's any questions. That's just kind of, this is how physics problems usually feel. There's a bunch of kind of playing around, playing with your equation, looking for something. And once you find something that gives you the first piece of the puzzle, then you can go and solve for everything else. Questions on that? Right on. Okay. How about any questions on any of the plotting stuff? Or did anybody have any questions about the plotting? Tell you what, go ahead and you can start taking your break. Come back at 1:45 for the group activity, or try it here at 1:43. You know, you were all stressed out about not having enough time for the group activity. So hopefully you studied that other stuff, those questions, and then make sure you're here on time and ready to rock. Okay. And if you want to keep working on this problem, do it. I'm going to try to set up some breakout rooms right now as best I can. Okay. So it's going to take me a few minutes. I'm going to turn off my monitor. I am still here, but you could take a break at 1:45. The group activity starts. All right. So I did get those rooms open. You don't have to join them right now. Yeah. So I'll be right back at 1:45. I'll just tell everybody that in the message. Any questions, anybody? Doing all right? Okay. If you want, you could get your Canvas site open so that you have the activity. The group activity is in Canvas again. So, and you could make sure you have that right there. And then I think it opens up at 1:45. I'll confirm that on my computer too. Let's see. Early section. Yeah, 1:45. Okay. All right. So a lot of you are probably getting ready to go here. I'll repeat myself after this, just in case somebody's coming in late or isn't here right now. But if you open up Canvas right now and make sure you can find the group work in the week 2 section, I'll do a screen share. So let's go back to here. Let's see. So somewhere in the week 2 module here, if you scroll down, you guys should have this visible to you. Group work, week 2, early section. All right. And so I've got you set up. Now, I think there might be one student that's from the late section because of a time conflict. Just join in and I'll deal with that. All right. So turn it in, and it might take some more work on the back end, and it might take some diligence on your part confirming I type things in. But so that's where you get it. And when you go there, yeah, just most of the points are for turning in something on time. There's points for following directions as well. So, yeah, it's more important that you work together and try to learn from this than necessarily getting the right answer. The right answer will probably be worth points this week, but I'm going to be looking at your procedure. All right. So it's all about working and getting something turned in. Now, yeah, so you can work on a paper right in front of you and at least be talking in the breakout room. And then you could say, this is what I got. This is what you got. And then you could turn in whoever you think has the best. And you can turn in one document for everybody. Again, you could turn in one document for everybody. Oh my gosh, come on. There we go. All right, so you could turn in one document for the entire group. You don't have to each turn it in. Now, if you want to each turn it in, I realized something today was when I make comments and you don't have the work turned in, it's maybe a little bit confusing when I'm doing some of these lab reports. So if you have the time, turn it in. And remember, at the end of class at 2:15, stop working. The next 15 minutes are for turning it in. If you try to push the limits and don't get it turned in, everybody gets a 0. I don't care. Okay. So don't try to push it and say, oh, I don't care. You will get a 0 if you turn it in late. All right, go to your rooms and get it done. And if you don't have a group yet, I'll put you in one here. Let me see. And I see some, okay, so let me get, though, you guys are in 3, I think. Is that, okay, so Trinity's extra one is in 3. I'll get you there. And then Olivia, let's see, I'll get you into, where was Olivia's one? Wait, where was it? Olivia, I think I'm going to put you in 4. And then Isaac, you were in one, I think, already. Right? Oh, okay. He's got one. Nick, let me get you in a room here. Were you in a room before? Do you know or not?
No.
Okay, let me just put you in 8. It doesn't matter. Okay, there we go. What's going on, Olivia? Is everything okay, or is it just crapping out on you?
I think my Zoom isn't working. It's kind of.
I gotcha.
Right now.
Well, Olivia, if you need to just call them, like get in there and get their phone numbers and call them and talk to them or something. But let me put you in there anyways. All right.
Okay, thank you.
What room were you? Do you remember? I think you were 4.
4. Yeah.
All right.